Hello everyone, welcome to our video lecture on the 5th chapter of Formal Logic Primer. This is the chapter on the long truth table method for checking the validity or invalidity of an argument. So this is really a chapter where everything we've been doing so far comes together. And then we're going to see chapter 6 is really just a kind of shortcut way of doing what we're doing here in chapter 5. So now we should be hitting our stride, even if you were working through the other chapters and struggling a little bit just to see how it's all going to fit together. This is where all those pieces should come together and hopefully make a little bit more sense if they didn't beforehand. So, oh, I've cut off the title there with my picture. Okay. So, this long truth table method, this is a very short chapter. In fact, there's not a lot to really say in terms of what new we need to learn here. It's actually really quite simple. We're just taking everything we've been doing so far, pulling it together, and then finally doing something with it. So what is this method? Well, to really understand what the method is and what it is we're doing, we have to reach back to some of the very first things we were learning about deductive arguments, which is the distinction between formal validity and invalidity. Right? So in a valid deductive argument, formally valid, but in a valid deductive argument, the truth of the premises guarantees the truth of the conclusion. Right, remember that. That's really the characteristic feature of a deductive argument, that if it's valid, the truth of the premises guarantees the truth of the conclusion. Unlike an inductive argument, which can be a good argument. You can have a sound inductive argument, that's true premises. Those premises really support the conclusion. They give you some good reason to believe the conclusion. And the conclusion can turn out to be false. Right? That's just not the case with a deductive argument. In a deductive argument, if it's put together the right way, it's a valid argument, it's truth preserving, then if the premises are true, the conclusion absolutely has to be true as well. For the premises to be true and the conclusion to be false involves some kind of contradiction if the argument's valid. That's really the key. So the truth table methods, we're learning the long truth table method here in this chapter. The next chapter is the short truth table method, sort of a shortcut truth table method, is a kind of tool that lets us check deductive arguments for their validity or invalidity. So all deductive arguments are either formally valid or formally invalid. And by using the long truth table method, we can really exhaustively check whether or not a given deductive argument is valid or not. Now, the truth table method is quicker. We don't have to do as much work to see if an argument is valid or invalid. But to be able to use the short method, you really have to understand how the long method works so you know what you're trying to do. And one disadvantage with the short method is that it's a little bit easier to make mistakes. So if you've been learning how all these various parts of statement logic work as we've been working through these chapters, if you really have a firm understanding of it, and you put together a long truth table and you don't make any mistakes in terms of filling in the values or having the right number of columns or rows or something like that, you should be able to tell with 100% accuracy whether or not a given deductive argument is formally valid or formally invalid. Now, that's always the key, not to make a mistake along the way, which it can be very easy to do when you're filling in a whole bunch of true and false values in a bunch of cells. You know, your eyes can kind of go funny. It can be a little hard to read sometimes and keep track of. But as long as you pay attention, you're careful with what you're doing, the long truth table method is an exhaustive way to check whether or not an argument is, a deductive argument is formally valid or formally invalid. So there are really 3 steps for using the long truth table method. This is on page 53 of the Formal Logic Primer. But basically just copy and pasted straight out of there. I've made just a couple of little tweaks here on the slide, but it doesn't really change any of the substance. So the first step, when you have some argument and you want to use the long truth table method to check it for validity, first construct a truth table that fully diagrams the argument to be tested. What does this involve? Everything we've been looking at so far. So assuming the argument starts in natural language, right? It's just normal spoken or written English. First, we need to translate that. We need to translate everything that's going on in the argument into simple statements. For that, we have to follow what we were learning in the first chapter. Right? We have to break it down into the smallest little bits we can that are still able to be true and false. We're going to have to assign those letters. We then have to construct a truth table And this is really where chapter 2 comes in handy. Chapter 2 outlined how to do that, how to have the right number of columns and rows, how to fill in the simple statement values. Now, chapters 3 and 4, those really telling us about operators, how to symbolize our simple statements. So once we have the argument, we've broken it into those little simple statements, we need to sort of stick them back together to show how they connect to one another. That's what the operators do. And also learning those operators help us fill in all of the values on the truth table. So chapter 2 outlines, we need to, the last step is fill in the truth values for the complex statements. And it's only by understanding in chapters 3 and 4 what the truth conditions are for those complex statements and how those can vary when we start using brackets to string them together and make even more complex statements. That lets us, gives us all the information we need to be able to fill in our tables. Right? So really chapters 1 through 4, everything we've been doing so far, it all comes together here in chapter 5, and now we can make use of all of it. We can see ultimately what the point is. Second, so after we've made a full truth table, right? We want a truth table that diagrams the whole argument, has all the statements, all the simple statements, all the complex statements, the conditions under which they're all true and false. Now, what are we going to do here? Well, something we've largely set aside is labeling the premises and the conclusion in an argument. We've just been working with statements, looking at how to translate those, how to symbolize them, how to represent them on the truth table. Now that we're using the truth table method, we actually need to label those premises and the conclusion of the argument. Why? Because now we're going to be interested in picking out certain rows on our truth table. So the truth table as a whole shows us all the times when a statement is true or false and why it's true or false. Once we have the truth table made, we want to examine, we want to take a look at each of the rows where the conclusion is false. Just ignore rows where the conclusion is true. Now, depending on what the conclusion is, you might be ignoring half or even more than half of the rows on the truth table you made. That might seem, in some sense, sort of redundant. It's like, why did we make all those rows if we're going to ignore a bunch of them? This is exactly what the short method is trying to do. It skips making the rows you don't need, but we really have to go through the long method to understand what rows we need to be looking at. Right? So in the long truth table method, construct the full truth table the way we've been talking about, and then just simply look at all the rows where the conclusion is false. Just don't worry about rows where the conclusion is true. Third step. Read across each row where the conclusion is false to check the truth of the premises. So we're going to have in our columns our premises and our conclusions marked. We go down and look at each row where the conclusion is false, and then we check in that same row to see whether or not the truth value of the premises, whatever those were, whether they're simple or complex statements, we're looking to see if the premises are true or false. Now remember, in a valid deductive argument, in a formally valid deductive argument, the truth of the premises guarantees the truth of the conclusion. So what does that mean we're going to be looking for? Well, it means we're going to be looking for this. If you find a single instance where the conclusion is false and all the premises are true, then you have an invalid argument. Why is that? Well, like I just said, a formally valid deductive argument is truth preserving. The truth of the premises guarantees the truth of the conclusion. That means it's impossible to have an instance where all the premises are true and the conclusion is false in a valid argument. So if we find one of these cases where all the premises are true but the conclusion is false, then the argument just isn't valid. And this is what the truth table is doing. It's showing us all the possible combinations of true and false, how all of the statements that make up the premises and the conclusion could be true or false, all their possible combinations. And then we're looking through all those possible combinations to see if we can find an instance of invalidity. That's exactly what this is. If you find an instance where the conclusion is false but all the premises are true, you found at least one place, one time, where the truth of the premises doesn't guarantee the truth of the conclusion, so the argument is invalid. Now, if you can't find that, if every time you find the conclusion is false in some given row, there's always at least one premise false, then the argument is valid. Why? Well, because the truth of the premises is guaranteeing the truth of the conclusion. Anytime the conclusion is false, at least one of the premises is false. So you just never find an instance of invalidity. An instance of invalidity is just where all the premises are true and the conclusion is false. That's really what we're interested in. Right? Now, what are we not looking for? Well, we're not looking at places where the conclusion is true. In a valid deductive argument, the truth of the premises guarantees the truth of the conclusion. Now, that doesn't amount to the same thing that anytime the conclusion is true, all the premises must be true as well. Right? So there can be cases where one or more premises are false and the conclusion is true, but we don't really care, because validity is really this statement that's, or this property that's saying when the premises are all true, the conclusion has to be true as well. So we can try to rule out instances of invalidity just by looking to see if there's ever a case where all the premises are true, but the conclusion itself is false. Now, that's it. That's all there is to this chapter. That's, in some sense, we've been, making a cake or something, and this is the cherry on top. Now we've got this tool at our disposal. The truth table, in a sense, really is the tool. Translating the natural language into simple statements, symbolizing how those statements fit together, how they connect with each other, representing that all in the truth table, setting that all up gives us what we need to then go ahead and check the rows we're interested in to see if we find the situation where the argument is invalid. If we can't find at least one instance where it's invalid, then it's valid. So let's just look at some examples now. Let's start working through this more. And so in this video, I'll try to work through some relatively simple arguments and just how those fit on a truth table. I've constructed different examples here than I have in the book, just so there's more variety, more things to read, more things to look at and think about. On the video for Friday, I'll try to make things a little bit more complex. I'll introduce some instances where we have really complex statements that are using brackets. So Friday's video is really just going to be more examples like this, working through them, just showing how the truth conditions differ and how the truth table shows that to us. So I've got 3 examples we're going to work through in the rest of this video. And we'll really do the whole thing. So we'll start with natural language. We'll translate that into simple statements. We'll symbolize the simple statements. We'll have a symbolic representation of the argument. We'll then make a truth table that represents how the argument functions. We'll then check on that truth table whether or not the argument is valid or invalid. So we're really working through everything we've done in previous chapters. Now, one thing I'm not going to do is really walk through in chapter 2. There are those different rules for truth table formation. If you follow those steps, you should always get things right. Why am I not going to follow them? Well, like I said back when we were doing it, really the first, I think, 4 steps. Once you get a good handle on exactly what it is you're supposed to be doing, you can, in some sense, just do all those steps at the same time. You don't even really need to think about them as separate steps. It just sort of turns into one sort of complex task that you're doing. So hopefully that's not too confusing. If you'd really like me to work through those steps, please let me know, and I'll try to do that in the next video or the ones next week. But I'll walk through what it is I'm doing as I'm doing it, and hopefully you can see how the rules outlined in chapter 2 really capture that. Okay, so our first example, all right, and I'm sorry these examples are a little bit boring. I find that can be pretty useful when you're learning something like this, just so the examples aren't too distracting. So look, if I'm making this video, and this is me, right? These are my words, I'm speaking. So of course, one thing we're supposed to do when we translate is avoid pronouns. So this is me talking here, right? If I'm making this video, if Carl's making this video, then I'm being recorded. So I'm being recorded because I'm making this video. It's pretty obvious, right? This is a very simple argument. We've really got 2 simple statements. Carl is making the video on chapter 5 of Formal Logic Primer, right? The I'm making this video. Well, who's I? Well, it's Carl, right? What's this video? Well, it's really the video lecture on chapter 5 of Formal Logic Primer. So remember back in chapter 1, something we're supposed to do when we translate from natural language into statement logic, we're making our simple statements, one thing we're supposed to do is avoid pronouns. So we want to try to make things as clear as possible. So In this case, my translation is actually longer than the natural language statement. And this is exactly part of why we do what we do in natural language, is to try to efficiently communicate things. We try to communicate and save time and energy, and often context and the use of short forms, things like pronouns and so on, really help us communicate what we mean in a way that people sharing our context will hopefully understand. And it's just easier. It takes less words, fewer words, less time and energy than actually spelling out exactly what we mean. Now, of course, when we're trying to do logic, we're trying to pay very careful attention to exactly what we mean and whether or not it's true. So sometimes we have to take more time and energy, try to make things as precise as possible. There will be some details that we might ignore. We're going to see that in the next couple of examples. And sometimes there's extra detail that we need to stick in there to clearly capture the meaning of what's going on. Now, if you didn't know, if you just had this natural language statement, if I'm making this video, but you didn't know it was me, Carl, who's saying it, that I was making this video that you're watching right now as I was writing or uttering that, you probably wouldn't be able to make the translation I just made here. If all you had is somebody, right, said, if I'm making this video, you might not be able to replace I and this video. You might just be stuck with the simple statement, I am making this video. Right? Or I'm making this video. A contraction's fine. There's really no harm there, as long as the meaning is still clear. If you know who said it, but you don't know what the video is, then you should replace I with a proper name. Say it's, I don't know, Sarah. Sarah somebody, right? Sarah somebody has this on Facebook or something. If I'm making this video, then I'm being recorded, right? Then you could translate that, Sarah is making this video, right? If you knew what the video was, you should replace this video with something more precise. So always go for more precision if you can. So we have M, right? Now, if we look through here, there's really only one other simple statement. Carl is being recorded. So if we take a look at the natural language version again, and then we look at what we have here, what we really have is if Carl is making the video on Chapter 5 of Formal Logic Primer, then Carl is being recorded. So Carl is being recorded because Carl is making the video on Chapter 5 of Formal Logic Primer. Right. Now, what does that amount to in terms of the argument? Well, this actually is an argument form we've been working through, and you're going to see that the truth table for this argument's one we've already encountered back in Chapter 3. The argument's actually quite simple. It's what we call a modus ponens argument. It has an implication statement, right? If M, then R. If Carl is making the video of Chapter 5 of Formal Logic Primer, then Carl is being recorded. As a matter of fact, Carl is making the video in Chapter 5 of Formal Logic Primer. Conclusion, therefore, or so, Carl is being recorded. Now, if you look at the natural language version, right, what we have is really the first sentence represents our first premise, if M, then R. The second sentence, though, doesn't represent the order of what we see. In the second sentence, if we're just trying to understand that in terms of what statements, what we actually have there is so I'm being recorded. It's really so R, right? So conclusion, Carl is being recorded because Carl is making the video on Chapter 5 of Formal Logic Primer. So if you just look at the natural language, we really have this order. If M, then R, R, M. Right? That's really the sequence that's there. What we have is that inference indicator, so, that indicates that R, right, Carl is being recorded or I'm being recorded, is actually the conclusion. Now, in this case, the conclusion comes before a reason that's being given, right, because I'm making the video. And now we might look at this and say, oh, this is actually an explanation, not an argument. Sometimes this happens, right? Whether or not something is an explanation or an argument, it can really depend on context. The same thing being said could be one or the other. It really depends if the speaker or writer is trying to convince somebody with reasons, or they're just making some statements they assume other people are going to take to be true. Right? So let's just assume this is an argument. So we'd have it represented this way. If M, then R, M, therefore R. So look, we've done our initial work. This is really what we need to do in chapter 1. And now that we understand how the different operators work, we can fully symbolize the argument. So we've got the symbolic representation, we've got 2 premises and a conclusion. One tip for the final homework assignment, where you have to find an argument, translate it, symbolize it, provide a formal representation of the argument like this, right? What's symbolically what's going on in the argument, then make a truth table and check it for validity. Try to keep it simple. Try to only have an argument that has, I'd say, no more than 3 simple statements in it. You can have one with more, right? And so there's nothing inherently wrong with having an argument with 5 or even 6 simple statements. I recommend don't go beyond 6. Probably don't go beyond 5, sorry. Yeah, having something with 3 or 4 or 5 simple statements is okay. But even with 5 simple statements, all of a sudden you're up to 32 rows. That's a lot of rows. That's a lot of room to make some simple little mistakes that might cost you marks. And I don't want to see that. So it's fine to pick a very simple argument like this one, right? Of course, you've got to go out in the wild and find one. But try to find some very simple reasoning where there's only 2 or 3 different statements and somebody is trying to reason about how they fit together in a way that we can charitably construe or interpret deductively. Right? So now let's take a look. So we've got our symbolic argument. And this, once we have this, right, once we've translated, we've got our symbolic form, we've got premise, conclusion, and we've got our letters and our different symbols. This is where, in previous chapters, I was saying, in some sense, the world sort of fades away and we can just focus on the relations between the statements. Now, ultimately, we want to use this as a tool and actually apply it to thinking in terms of natural language, which we can do. But to do our truth table and to check for validity or invalidity, in some sense, it doesn't matter what the natural language was. All that matters is how the various statements connect to each other. What the simple statements are, what the complex statements are, what the operators are, what acts as premises and conclusions. We're going to see that really any argument of this form, if M then R, M so R, this is actually a valid argument. And I know that ahead of time. Right? There are certain valid and invalid argument forms where any argument that fits into the right kind of form is valid or invalid. Learning to do what we're doing here is helpful because then any argument you encounter, you can do this kind of work, and if it's a deductive argument, determine whether or not it's valid or invalid. Okay, so we've got our argument here. I've just sort of put it across the top. Now we're going to go ahead and switch over, and I'm going to do it this way. We're going to switch over into Microsoft Word just to work through how we actually construct the truth table here. And then we'll switch back to the slideshow. I have the truth table set up there already, but we'll work through how to make it as practice on doing everything we've been doing in the previous chapters. And then we'll come back to the slideshow, sort of see just what's going on there, and then we'll work through our next 2 examples doing effectively the same thing. So here we are in Word. I've skipped ahead to the 3rd examples. Let's go back up to the first one here. Carl is making the video on Chapter 5 of Formal Logic Primer. Carl is being recorded. And of course, here's the symbolic representation of our argument. Right? Now, I didn't put the natural language back in here. I could have, but just for the sake of trying to keep the screen fairly minimalistic in terms of what's going on, this was our argument. If M then R, M so R. Right? So we need to go ahead and insert a table. So we go up to Insert, we select Table. Now, like I said, you can start with really whatever table you want. You can add columns and rows to it. Depending on how much is going on in the argument, you might be able to tell ahead of time how many columns and rows you need. So just taking a look at this one, a little bit of a mental shortcut. Really all I need to do is construct the truth table for an implication statement. That's really all this argument requires, right? What do we have? We have 2 simple statements, M and R. We have 1 complex statement, if M then R. So all we need, when we think about it, so we have 2 simple statements, so we need 2 columns. How many complex statements do we have? Just 1, so we need a 3rd column. How many rows do we need? Well, we need 2 to the power of n, where n is the number of simple statements in the argument, which is 2. 2 to the power of 2 is 4. So in addition to the header row, which is what I'm starting with here, I need 4 more rows. So I'm going to have a total of 5 rows and 3 columns. Let's go ahead and put those in. And then what's that going to look like? Well, now I need to start filling in. So I need a column for M. That's one simple statement. I need a column for R. I need a column for if M, then R. And I'll go ahead and I'll just stick those in bold, and I'll put some shading in there just to show it. Now, when you're doing your own homework assignments or writing the final exam or something, you don't need to shade the header row. You don't even have to put it in bold. It is nice to do something to show that the header row is different from the rest of them. But anybody who is looking at your work and grading it is going to assume that first row is just the header row. And so one tip there shouldn't be any true or false values in the header row, right? That first row shouldn't contain T's or F's, though it can, of course, contain T or F as a simple statement letter. So look, let's start filling in our table here. Oh, one last thing. So I actually forgot this one momentarily. So we've got our header row. We need to label our premises and our conclusion this time, because we actually have an argument we're dealing with. So I'll just label them in order here. So premise 1 is over in our last column. Right? If M, then R, that's premise 1. Premise 2 is just M. So we'll find M. It's back in the first column. And we'll say that that's P2. The conclusion is R. Right? It's the conclusion of the argument. So we'll go ahead and we'll label the column for R the conclusion. That's going to matter once we fill in our truth values. So we need to fill in the truth values of the simple statements just like we've done before. So we can use either method. We can start at the left and move to the right, or start at the right and move to the left. I'll start at the left and move to the right this time. I'll do the first method. Maybe in the next example, I'll try to start at the right and move to the left as long as I remember. So when we start, we fill in half true, half false for the number of rows we have. We only have 4 rows, so that's just 2 truths and 2 falses. Look at that. First column's done. Next column, we have the number of truths and falses we put in at a time, and given that this is the last column that represents a simple statement, we just know it's going to alternate between true and false. So we've got true, false, right? 1 true and 1 false at a time. Now, to fill in the truth value for our complex statement here, if M then R, we need to look back to the truth values of M and R and remember under what conditions if M then R is true. Now, an implication statement is true so long as, okay, I'll put it the other way around. An implication statement's only false when the antecedent is true and the consequent is false. Why is that? Well, that's true because an implication statement is only trying to tell us if the antecedent is true, then the consequent must be true as well. In this case, that means all the statement is saying is that if M is true, then R must be true as well. It's not telling us anything about the situation where M is false. So anytime the antecedent is false, the statement's true. As long as both the antecedent and the consequent are true, the statement is true, the complex implication statement. It's only when the antecedent is true and the consequent is false that the implication statement is false, because the implication statement is telling us exactly it cannot be the case that the antecedent is true and the consequent is false. Okay, and if that's, seems odd or unusual or not fully clear, go back to chapter 3 and review the material on what implication statements are, what the truth conditions are. Take a look at the text, take a look at the video, take a look at the slides, right? That's really where we work through that material. So now in filling in our truth values in the cells in the column here that represents the complex statement of M then R, we just have to look at M and R. As long as we don't have a situation where M is true and R is false, then the statement if M then R is true. So in the first row, M is true and R is true. So the statement if M then R is also true. Second row, M is true but R is false. So the statement if M then R is false, because that statement is just saying if M is true, then R has to be true. And we have in the second row, M is true but R is false. So we would just be contradicting ourselves if we say if M is true then R is true, And here's a situation where M is true and R is false, right? Something's got to give, right? Either M is true and R is false, and it's just not the case that if M is true, then R has to be true. Or if M is true, it's true that if M is true, then R has to be true. Then it can't be the case that when M is true, R is false. So this is why it's the statement if M then R is true in this, or false in this row. Now, in the last two rows, if we just look over at the column for M, we see that M is false in both of those rows. The antecedent is false. So the implication statement that takes M as the antecedent is going to be true because M is false. Right? And that statement, if M then R, just isn't really telling us anything about the situation where M is false. It just doesn't really care about that situation. So the statement can still be true. So look, we've got our table. This is a full table, truth table that diagrams everything that's going on in this argument. We've got all the possible situations. We only have two simple statements, so there's only 4 possible combinations of their truth values, right? They're both true, they're both false, or one or the other is true, while the other one's false. That's what the 4 rows show us. We know that in 3 of those 4 rows, the statement if M then R is true. So now we need to move on to our last step. What are we doing? Well, we're looking, the second step of the long truth table method, we want to identify the rows where the conclusion is false. Now, the conclusion of this argument is R. Carl is being recorded, right? That's represented in this middle column. Depending on the argument, where the premises and conclusion are going to show up in different places. This argument has a simple statement as a premise and a simple statement as a conclusion. Some arguments don't. Some arguments will have only complex statements as premises and conclusions. But we still need the simple statements on our table to see when the complex statements are true or false. So what matters is that we identify the column that represents the conclusion. In this case is that middle column representing R, because R is the conclusion. We then need to identify each row where the conclusion is false. In this case, and I'll add a little bit of shading here just to show what's going on. In row 2, the conclusion is false, and in row 4, the conclusion is false. Right? Those are the 2 rows we care about. So we can just ignore the other rows. Right? They don't matter anymore. I'll do this just for a demonstration. Right? We can just delete those rows. Now, don't actually do this in practice. Right? Don't do this, especially when you're doing your homework assignment, when you're doing the final exam. Don't delete that content. We want to see that content in there to make sure you're getting it all right. I'm deleting it here just to show that it doesn't really matter what's in those rows anymore. What we really want to see, what we want to focus on, what we want to look at, are the rows where the conclusion is false. Those are the only rows that really tell us whether or not the argument is valid or invalid. Now I'm going to put back the rows I deleted. As I said, I just wanted to delete them just to show that they don't really matter, right? We're just focused on these rows where the conclusion is false. So now that we know it's rows 2 and 4 where the conclusion is false, we need to check the premises in each of those rows to see if there's ever a situation where all of the premises are true. In this case, there's 2 premises, so are both premises true and the conclusion is false? If we find that, then the argument is invalid. If at least one premise is always false when the conclusion is false, then the argument is valid. So if we look through on just row 2, take a look at, let's look at it in the order of the premises. Let's do it that way. So premise 1 is represented over by the right-hand column, if M then R. And in row 2, premise 1 is false. Right? Now we can look over at premise 2 and we see premise 2 is true. Right? Now, it doesn't really matter how many of the premises are true if at least one of them is false. Then the row doesn't show us invalidity. Why? Because in this row where the conclusion is false, at least one premise is true. If an argument is formally valid, we have a guarantee that if all the premises are true, then the conclusion must be true as well. That said differently, it's impossible for the conclusion to be false while all the premises are true. In this instance, we have a false conclusion, but not all the premises are true. So we haven't broken our guarantee, right? So this particular row, this combination, doesn't show us invalidity. Let's move to the 4th row. We've only got 2 rows to look at. we'll take a look at P1 again. In this row, P1 is true. Right? The conclusion false, P1 is true. What about P2? Premise 2. Premise 2 is false. Right? So look at that. Now, we're done. We're finished here. The only thing left is to make a statement. And so when you're thinking about the exam or the homework assignment where you've got to work through something like this, now that we have this here, we can judge whether or not this argument is formally valid or invalid, right? And which is it going to be? Well, in each row where the conclusion is false, at least one premise is false. That means that this argument is formally valid. So we can say that, oh, I've got caps lock up. This argument is formally valid because in each row where the conclusion is false, rows 2 and 4, at least one premise is false. P2 in row 2 and P1 in row 4. There. That's it. We've determined whether or not this argument is valid or invalid. This is a valid argument. If the premises are true, the conclusion has to be true as well. Why is this useful? Well, now in terms of actually evaluating this argument, when we think back to Hughes and Lavery and we think about the criteria we have for evaluating an argument. Are the premises acceptable? Are they likely true? Right? Are they relevant to the conclusion? Are they adequate to support the conclusion? By knowing that this is a formally valid argument, we can say with certainty that the relevance and adequacy criteria are met. Right? This argument meets those two conditions for a sound or a good argument. The only thing we have to wonder about now is whether or not the premises are acceptable. So in this case, if we look at the premises, not just the simple statements, but the premises, right? We've got 2. If Carl is making the video on Chapter 5 of Formal Logic Primer, then Carl is being recorded. Do we think that's true or false as a statement about the world we live in? Yeah, I don't know how you make a video without being recorded. I just, to be recorded is to be put on video, in a sense. That almost seems analytic, right? Is it true, right, or probably true enough that Carl is being recorded? You know, presumably the time here is right now. We're talking about the present. Well, by the time you watch this, it'll be false. But at the time I'm making the video, I am in fact being recorded, right? So when we look at those premises, right, is if M then R true? Is it likely true? Is it acceptable? More likely true than false? Right? Now, ultimately, formal logic, statement logic, what we're looking at is really only interested in exploring the conditions of whether or not the statements really are true or false. In some sense, it doesn't really care about the limits on our knowledge and that we can't know for sure whether or not lots of things are true or false. So there is still that degree of uncertainty when we're evaluating whether or not premises are true or false. If we have empirical statements, things that could be true or false, you know, we've got synthetic statements, generally speaking, empirical ones, statements about the world we live in that you need to go out and check somehow to verify or falsify. There's still that degree of uncertainty because we might think something's true and just be wrong about it. Now that said, what formal logic, what statement logic really helps us with is just showing the relationships between different statements and different pieces of arguments depending on what's true or false. So once we come to discover whether or not some particular fact, you know, some statement is true or false, we can see, in the sense, the domino effect or the ripple effect of how that's going to impact whether or not a certain conclusion is going to be true based on that statement. So in this case, we've got a formally valid argument. The premises are acceptable, right? They're true, unless, I don't know, I'm dreaming or something. Those premises are true right now. So let's go ahead and switch back to our slideshow for the moment. I'm just going to stick the results of what we were doing here up on there in part, so when I post those slides, you can see the result that we've worked through and ultimately achieved. And you can go back to this recording, right, go back to the video and see how we actually got there. But I'm just going to put that up. So let's switch back to the PowerPoint presentation. So we've got our argument there. We want to put that up on a truth table. So here's our truth table, right? It's exactly what we just constructed. And of course, we've got in row 2, the conclusion is false, but we have at least one premise false. And in row 4, the conclusion is false, but one premise is false. And so, because at least one premise is always false when the conclusion is false, this argument is valid. Right? There, that's it. We're done. Now, let's take a look at example 2. All right, so the second example, and this again is just an example from my life. I've got some apples in the fridge and I've been thinking about making an apple crumble. So here's my argument. I'll make an apple crumble today as long as I have the time to do it. I won't have the time, so I guess I won't make it. All right, I'm not sure yet if I'm going to have the time. I don't really see how it's going to fit in my schedule, but I really like to make one. It sounds delicious. So what do we have going on here? Well, when we look through it, you know, what really matters here in terms of the translation? I'll make an apple crumble today. Well, that seems important. You know, make an apple crumble today. Carl's going to do it. I'm the one speaking. As long as. Well, that sounds familiar. What does that seem like I'm trying to say? That sounds like a biconditional. Right? As long as I have the time to do it. So in our translation, right, what's going on here? Carl will make an apple crumble today. You know, and I could say when, you know, Carl will make an apple crumble on Wednesday. It's the day I'm actually making the videos. Maybe that's maybe what I should say. Of course, depending on when you watch it and so on, the referent of today might change. This is part of the problem with pronouns. So Carl will make an apple crumble today, whatever day it is, as long as he has the time to do it. So if he doesn't have the time to do it, he won't make it. And that's really what the conclusion is, right? It's saying, I won't have time. Carl won't have the time to make it. So, you know, I guess I won't make it. Does the guess really matter here? Does that really affect any of the truth conditions? No, it seems like what I'm really trying to say is I won't have the time to make the apple crumble, so I will not make the apple crumble today. That seems to be really what I'm getting at. We do this all the time. We stick in other words, often little, in some sense, distractions from the truth conditions. We'll stick in a little, I guess, or whatever, just in some sense, filler words, words that don't really change the truth conditions of what we're trying to say, although sometimes it seems like they might. Right? So there's an interesting question why it is we say what we do and what we're doing with language, assuming we're just trying to express factual statements, right? Statements that are either true or false, and really if we're asserting a statement, we're saying it's true. Then all that filler we can just try to get rid of, unless we think it's really relevant for the truth conditions. And this is where claims about probability might matter. So let's take a look at the translation. And here again, I'm starting to mix it up in terms of what letters I'm using. So instead of just using P and Q all the time, look, let's use A for Carl makes an apple crumble today. And again, it could be Carl makes an apple crumble on Wednesday. Right? Could be Carl makes an apple crumble on Wednesday, March, what is the day? 25th. So A, Carl makes an apple crumble today. T, Carl has the time to make an apple crumble today. Now, if we look back to the natural language, there's the, as long as I have time to do it, time to make the apple crumble, I won't have the time, right? There's a negation there. Remember, whenever we're translating, we want to translate our statements to be positive statements. They're talking about what is the case or what does happen, and then we can negate that if we're trying to show what isn't the case or something that's false, right? Something that's not happening. So our symbolic representation of the argument. Like I said, we've got a biconditional. Like Carl will make an apple crumble today as long as he has the time to do it, right? So if A, then T, right? If A is true, then T is true. And if A is false, then T is false. That's really what the biconditional is saying. They're either both true or both false. It's either both true that I have the time to make the crumble and I make it, or I don't have the time to make it, so I don't make it. Really what I'm saying is it's just not going to be the case that I have the time to make the crumble, but I don't make it, or I make it without having the time to make it. That one seems pretty obvious, right? But I'm saying as long as I have the time, right, I'll go ahead and make the crumble. Now, what's actually going on in that argument up top is that I'm saying not T, I won't have the time, right? It's going to be false that Carl has the time to make an apple crumble today. Conclusion, not A. It's going to be false that Carl makes an apple crumble today. Said differently, Carl doesn't make an apple crumble today. Carl's not going to make an apple crumble today. It's not the case that Carl makes an apple crumble today. And any other similar statement. Okay, so we've gone from natural language, we've translated it, we've symbolized it, we've got our argument in symbolic form now, we have our premises and our conclusion just in terms of the statements and operators. Now we need to go ahead, I gave away the game. We need to go ahead and make the truth table for it and show what's going on. So we'll switch back over into Word here. Same thing as before. I've got the translation. I've got the symbolic representation of the argument here. Let's go ahead and make this. So what are we going to need now? Well, we've got two simple statements again, A and T. So we need two columns to represent those. Maybe this time I'll just sort of start by, I'll stick in the two columns and sort of work through how many I need. So I know I got A and T, but if I look at the argument, I also have not T and not A. So I'm going to need a column for each of those because each of those statements is a complex statement. And here, I'll even start filling in as we go, just so everything becomes more clear. So I've got A, I have T. I also know I'm going to need not A. I'm also going to need not T. I also have one other complex statement here. A biconditional T. And I'm just going to copy and paste it. Getting the biconditional in can be a little tricky. You usually have to go to like insert symbol and find it, or you can use a key command for it. If you just, when you're doing your assignment and exam, if you just do a sort of the, you do that, we'll assume that's a biconditional as well. It's really the same thing. So arrows in either direction. Okay, so I've got all my statements now. I've got the simple statements. There's only two letters, A and T. So I need a column for each of those. I need a column for not A and not T because they show up in the argument. I also need a column for A if and only if T. Right? A biconditional T. So I need 5 columns for this argument to represent everything that's going on. How many rows do I need? Well, the number of rows isn't dictated by the number of columns. The number of rows is dictated by the number of simple statements. Every different letter is a different simple statement. So here again, we only have 2 simple statements. Right? So we need a number of rows equal to 2 to the power of n. I'm just going to write that here. By 2n. It actually needs to be superscripted, just to show it. Need 2 to the power of n. Of course, now I'm all superscripted. So n equals 2 in this case. We've got 2 to the power of n. What's that going to equal? And n is equal to 2 here. All right, I'm just going to leave it like that. It's going to be 4 again, just like in our previous argument. We only need 4 rows, even though this time we have 5 columns instead of 3. So I'm just going to add those. And again, if you just sort of go to the right spot on a table in Word, you can just click. There's the little add there. You can do it for columns as well. Or you can right-click and go to Insert. Right? Insert above or below for rows, right or left for columns. I need 4 rows. So 1, 2, 3, 4. I'm going to go ahead. I'll bold this top row. I'm going to fill it in just to make it look pretty. Now, last thing I need to do before I go ahead and fill in these rows with truth values, I need to identify the premises and the conclusion. Okay, so we've got P1, P2, and C. We've got 2 premises and a conclusion. Where do I fill it in? Well, premise 1, A biconditional T. So it's over here, so let's do that. P1. P2 is not T. Okay, fill that in here. And the conclusion is not A. Look at that, filled in. Now to fill in the table, we're going to start with the simple statements as always. And I promised last time I'd do the other method. So we'll start with the last simple statement, the one furthest most to the right. That's T. Again, we've only got 2. And we always know that last column alternates. So true, false, true, false. We then go 1 column to the left. We go to the A column. We're going to double the number of trues and falses we enter at a time and make sure we fill the column in. So we started with 1 true, 1 false. So now we're up to 2 true and 2 false at a time. So true, true, false, false. And that's it. We're done. We filled in these 2 columns. Now, We'll move over to the next column to the right. That's our complex statement, not A. Whether or not A is true depends on whether or not A is true. And remember, negation is just, has the opposite truth conditions of whatever's being negated. So whenever A is true, not A is false, and vice versa. So in row 1, A is true, so not A is false. Row 2, A is true, so not A is false. Row 3, A is false, so not A is true. Row 4, A is false, so not A is true. Same thing for not T, right? Anytime T is true, not T is false, and vice versa. So in this case, we've got false, true, right? Because of course, in the T column, we have true, false, true, false. So here we have false, true, false, true. All right, on to our biconditional. Remember, a biconditional is true whenever both of the logical units are either true or false. What the biconditional is saying is that it just can't be the case that one is true while the other one's false, right? They're either both true or both false at the same time. So in the first row, both A and T are true. In the last row, they're both false. So biconditional statement's true. In the middle 2 rows, one is true while the other one's false. So in row 2, A is true while T is false, so the biconditional is false. In row 3, A is false while T is true, so the biconditional is false there as well. Look at that. We have our table. Now we need to take a look at the column that represents the conclusion. That's this middle column again, the one for not A. Where is that conclusion false? In the first 2 rows. In that first 2 rows, the conclusion is false. So those are the only 2 rows we really care about now. Now we need to check the premises in each of those rows to see if the premises are true or false. In the first row, well, look at that. Premise 2 is false, right? Premise 1 is true. That's good for it, right? But as long as one premise is false, that's all we really need to care about. Right? So as soon as you find a premise that's false in a row where the conclusion is false, you can just move on to the next row. You don't have to check every single premise. In the second row, this time we have P2 is true and P1 is false. Now in the previous table, I was checking the premises in order, premise 1 and premise 2. It doesn't matter. All that matters is whether or not all of the premises are true or the conclusion is false. So it doesn't really matter what order you check it in. You should start by identifying the rows where the conclusion is false, precisely because those are the only rows you need to look at the premises in. But once you've identified those rows, as you're going through, right, you can just go row by row. If you have a truth table, if it has 4 or 8 or 16 or 32 lines, you just go through each line, check the conclusion first. If the conclusion is true, skip the row, move to the next one. If the conclusion is false, then start checking premises in whatever order makes sense, right? If it makes sense to just go left to right or do them in the number they're ordered, whatever works for you. Just go through. Okay, I've identified a false conclusion. Are the premises all true, right? Say you go through and you go true, true, oh, false. Okay, good. Next row, conclusion's false. That premise is false. Next row, conclusion is false. Right? All you're looking for is if you can find one row where the conclusion is false and all the premises are true, you've identified an instance of invalidity in the argument. Okay, let's go back to our slides here just to see that same result there. So we've got the same thing going on, same argument, right? A biconditional T, not T, so not A, right? We've got the same truth table here, and we have the same result, right? There's only 2 rows where the conclusion is false, rows 1 and 2. And each of those rows, there's a false premise. So this argument is valid, right? Because at least one premise is always false when the conclusion is false. This argument is valid. In the first row, premise 2 is false. In the second row, premise 1 is false. So because at least one premise is always false when the conclusion is false, this argument is valid as well. Okay, let's take a look at one more argument. I realize I'm already going over time, so I'm going to do this last one quickly. So I'm just going to sort of work through it. I'm going to explain myself a little bit less. Next day, we'll pick up and have some more examples to take a look at. So look, Sam won't learn logic if David is learning it. Either Paula or David are learning logic. So Sam won't do it. It should probably really be, either Paula or David is learning logic. Look, we got 3 statements this time. Sam learns logic, David learns logic, Paula learns logic. Those are really our 3 simple statements. What's the argument once we symbolize it? Well, it looks like this. If David learns logic, then it will be false that Sam learns logic. That is, Sam won't learn logic when David's learning it. Premise 2. Either Paula or David is learning logic. Conclusion, so Sam won't learn logic. Right? It's false that Sam learns logic. That seems to be what's going on. Right? Now, and one note on premise 1, and this had to do with when we're talking about necessary and sufficient conditions. So I represented premise 1 as if David learns logic, then Sam won't learn logic. Right? And if you look at this, our natural language statement, that's really what's going on, because we have if David is learning it. And of course, that the if signifies the antecedent. In the actual sentence, the antecedent comes after the consequent. That doesn't really matter logically speaking, right? We got to put those around. We have to have our if first and then our then, right? So if David is learning logic, then Sam won't learn logic. We could put that another way around. And don't worry about this if it's a little bit confusing. This is just to show that implication statements, you can represent the same thing a few different ways. So we can represent it if D, then not S. We can also flip that around and say if S, then not D, right? Potentially. We're not really told that here, but if Sam is learning logic, then it must not be the case that David is learning logic. Right? So if S is true, then it must be false that D. Now, that's saying something a little bit more than what we're explicitly told here. So we'll just set that aside for now, and if that was a little bit confusing, don't worry about it. So we've got this for our argument. What's that going to look like? Well, let's flip back over to our Word document where we've got everything going on. So look at that. We've got our symbolic representation of the argument. We've got our translation again. I'm just going to start with, well, that's unusual. So first, when we take a look at it, we know we have to have, well, we're going to have 3 columns. Why? Well, we need a column for D. We need a column for P, right? David, Paula, Sam. Right? We know each of them involves something. We've got 3 statements. What else do we have going on in the argument? Well, we've got an implication statement, a disjunction, and a negation. We should try to order the rest of our columns in an order of increasing complexity. So let's put the negation next, not S, right? Put that right after S. That makes it easy. So, right, when S is true, not S is false, and we can just compare them right next to each other. What should we put next to that? Well, if D, then not S. Why don't we put premise 1 there? Right now we've got an implication statement and a disjunction. They're both complex statements. Let's put this one here in part because we got not S right beside it. Make it a little bit easier just to look at it. And then finally we need P or D. Right? Either P or D. Okay. Now this time we have 3 simple statements, so we need 8 rows. 1, 2, 3, 4, 5, 6, 7, 8. Now we need to fill in our simple statement values. So again, we'll start just with the basic method. We'll go left to right. True, true, true. Oh, no R. True, 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 true. Right. 4 trues, 4 falses. We've got half of our rows is true, half of them is false. Next we go true, true, false, false, true, true, false, false. Then we go true, false, true, false, true, false, true, false, because it's our last simple statement. Great. So we filled in our simple statement values. Oh, and I forgot to do this. Forgot to fill in what the premises and the conclusion. Now, as you'll note from the fact that I forgot it, you can actually fill those in after you filled in the table. Strictly speaking, it doesn't matter. And this is part of why those rules that I outlined in chapter 2. If you follow the rules, you should never make a mistake as long as you're putting all the right values in everywhere. But there's some flexibility, right? Ultimately, you need the table constructed correctly. And if you do things a little bit out of order, that's okay. All right, so we've got our column for S. We have a column for not S. Of course, not S is true when S is false and vice versa. So we've just got the opposite values. right? Instead of true, false, true, false, true, false, we've got false, true, false, true, false, true. We've got this implication statement, if D, then not S. So we need to take a look at the column. My mistake. Hold on, I should have also given this some shading. In the column where D is true, we need to look at the column for D and the column for not S to see when the statement if D then not S is true. Remember, the statement if D then not S is only false when D is true and not S is false. So let's take a look. In the very first row, we actually see that. D is true and not S is false. So there's the statement if D is true, then not S has to be true is false. Now I'm just going to go quickly. It's the same truth conditions we've already been working with, right? So if I ever find that again, if D is true and not S is false, then their implication between them is false. Otherwise, it's true. So look, row 2, both simple statements, or both statements are true, right? D and not S. So this is true. Row 3, D is true, not S is false. So the implication's false. Row 4, both true, so they're both true. And then starting in row 4 through, or row 5 through row 8, D is always false. The antecedent is false, right? I got false, 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 false. So I know that the statement is just always true. Great. Now, P or D. So to figure that out, I've got to take a look at these two columns, the columns for P and D. As long as at least one of them is true, this complex statement, either P or D is true. It's also true when they're both true. So let's just fill that in quickly. Well, in the first 2 rows, both D and P are true. All right. Now we've got D is true in the next 2 rows, so this statement's true. P is true in the next 2 rows, so it's true. In the last 2 rows, P and D are both false, so the statement is false. Right. And one thing to note, our statement here is P or D. Now our columns aren't in that order, right? Our columns are D and then P. Does it matter? No, it just doesn't matter. Right? Oh, well, I also missed this up here. Okay. So now we need to identify all of the rows where the conclusion is false. Where's that going to be? Well, our conclusion is not S. So we'll start here. So in that row, it's false. So row 1, row 3, row 5, and row 7. Now we got to check premises. Row 1, premise 1 is false. Row 2, premise 1 is false. Right? And so look, I don't even need to look at premise 2 after I've identified that premise 1 is false in those rows. As long as there's one premise false, it's fine. Now, rows 5 and row 7. Uh-oh. Row 5, look at this. Both premises are true. Right? What does that show us? That shows us that this argument is invalid. I don't even need to do any more work. Right? This argument is invalid because in row 5, the conclusion is false while all the premises are true. That shows us this argument is invalid. As long as there's one instance like that, it's invalid. We don't even need to look at the rest of the table. Let's go ahead and switch back to the slideshow. And we're finishing up here. This is the last thing we're really going to do. Right? So we've got our argument. We've got our truth table. We've got these, in this row, okay, well, we've got true and false. And see, the table I made on the slide shows the complex statement columns at the end are switched around. The P or D and the if D then not S. They're in a different order. Does it matter? Not really. I made a choice about where to put them last time. It's important to keep all the simple statements together and have all the complex statements. It's good to have the complex statement increase in order of complexity so that they get more complex as they go. So you can move left to right as much as possible on the table, filling in truth values. But there's no big deal here. So this is going to look a little bit different than what I did on the Word document, but I get the same result. In row 5, both premises are true and the conclusion is false, and that tells me that this argument is invalid, right? Because we found at least one row like that. All right. Now, I know I've overstayed my welcome here. This video is a bit longer than it should have been. If you've watched this and this all makes sense, try doing the practice questions at the end of chapter 5. Next day, I'm going to do some more practice questions. So, maybe try to do some of them at the end of chapter 5. Maybe try to do 1 or 2, or maybe even do a handful, or try all of them. You might not be able to do all of them, because we didn't take a look at any arguments here that had really complex statements, that were using brackets to make the truth conditions more complicated. In the next video, we'll take a look at some example arguments that have that sort of complex structure to them, where we need to start using brackets and pay better attention to the truth conditions to see exactly what's going on. So see how to put that on our truth table and how to check that kind of argument for validity or invalidity. So thanks very much, and I'll see you next time. Bye for now.